So where he is? Oh, okay. This is his. But again, there is 10% for attending the class. If nobody shows in the class, I'm sorry, I will not give the 10%. I do not care if you watch it on online or not. Last time, professors came to my class, and it was the same situation, and they hurted me. They said, "Oh, why the students are not in the class? Oh, they're watching the class on the online. Oh, but this is not an excuse. They have to be in the class." So if you are not in the class, I counted for everybody how many times in the class, how he interact with me. If you are not in the class, I will not give you the 10%. You are losing 10%. So if you saw this guy, just let him know this. I will not tolerate that you will leave the class. Okay, guys. Okay, so welcome back to NE 630. Last time we talked about the flux measurements, or not measurements, flux definition or flux calculation inside the nuclear reactor. And we showed that last time that the flux in the fast region, to a good approximation, phi of A can be defined as chi of A divided by sigma total of A. Then this is in the fast energy region. This is in the fast energy region. Now, let's talk about slowing down region. Slowing down region. So last time I stated that this is the upper limit for the energy, and this is 0. And we said that the Stacy book states that this is at 50K EV. Again, some of the author, they will name it 50. Some other author will say that the cutoff or the separation between the fast region and the epithermal is just 100K. So this is the fast, this is the epithermal, and this is the thermal. So anyway, let's say from 1 MeV or 2 MeV up to 100 kilo electron volts, this is your fast energy region. So now let's look for the neutron moderation. Once you are born here in the fission energy region, you will start slowing down, and you will slow down in this epithermal region, and then you will reach to the thermal energy region. You will start thermalizing with the nuclei of the moderator. Inside this energy region, you will notice that the resonance is, if we have something like the cross section, for example, or actually we have to do it the other way. So the cross section, if you look for the cross section is like this, and you have maybe it's like this. Then you have from few electron volt to tens of kilo electron volt, you will have the resonance region, and the resonance region definitely is in the slowing down region. So this is the epithermal, and we call it slowing down region. So you will have the resonance absorption, the energy of the resonance absorption, usually this from few electron volt up to something like 10 to the power of 4 electron volt, 10 kilo electron volt or so. It will be in this region. So now let's look for moderation by hydrogen only. So if the moderator is just hydrogen, moderation by just hydrogen, by hydrogen only. So if we will consider a mixture of hydrogen, so what's alpha for hydrogen? A for hydrogen minus 1 divided by A for hydrogen plus 1 all square, and A for hydrogen is equal to what? 1. So alpha for hydrogen will be what? Will be 0. And let's assume that with hydrogen, we have different nuclei, heavy nuclei, but they do not contribute much to the slowing down like hydrogen. So those nuclei will have alpha j, where alpha j will be just aj minus 1 divided by aj plus 1 to the power of square. And if this is heavy nuclei, this will be around 1, because A will be a large number, so this will be around 1. So now we will try to write again the same balance equation as before. So the balance equation at energy here, energy E, let's assume that this is the energy E, and this is the energy of interest within delta E. Okay, within delta E. So the total absorption at this energy is sigma total as a function of energy E multiplied by the flux of E equal to, now I have to look for a scattering coming from E prime, and this will be E prime. So E prime might be here, E prime might be here in the upper energy region, but let's assume that I have sigma scattering, and this scattering is mainly coming from hydrogen, because I assume that the most important isotope to moderate the neutrons in this medium will be just hydrogen, and the other, or the rest of the other isotopes found in the reactor are high A material, so they will not contribute to the moderation. So this is sigma hydrogen as a function of energy multiplied by the flux at E prime dE prime. And this should be sigma scattering of E prime goes to what? Goes to E. So you have a scattering at E prime that will bring you to where? To E. But what's sigma scattering? Sigma scattering of E prime goes to E. This is what? 1 over what? 1 over 1 minus alpha. Yes, multiplied by what? E prime, which is the initial E prime, yes? So alpha is what? Is 0 for hydrogen. Is 0, so this will be what? And this will be multiplied by sigma of E prime. So this will be, yes, because sigma scattering of E prime goes to E is just sigma scattering of E prime multiplied by the probability that you will go from E prime to E. Yes, and the probability is just this factor, 1 over 1 minus alpha hydrogen multiplied by E. Okay, guys, so I have to divide here by what? By E prime. So this is this factor here is this. Plus, so this is the part I have to integrate from where to where? Huh? From any energy from E, yes, from E to infinity. Then I have to take the other contribution from the rest of the material, which is J does not equal to hydrogen. And this will give me the integration from E to E over alpha J. So you knew why I integrated from E to infinity here. Okay, why? Why I integrated from 0 to infinity?
Because one collision with hydrogen can lose all its energy.
Yeah, but okay. In order to come, this is Ibrahim. In order to come to energy E from yes, I can come from Ibrahim, yes, or I can come from here, or I can come from anywhere, yes. So if this is the terminal energy, the energy after the collision, if E is the energy after the collision, the initial energy should be what? E over alpha, because after one collision, you will multiply by alpha. Alpha will cancel with what? With alpha, and you will come to what? You come to E, yes? So if the final energy is E, this means that the initial energy should be E over what? E over alpha. So if alpha is 0 for hydrogen, anything over 0 is what? Infinity. Because if I come from infinity and in one collision alpha is 0, I can lose everything up to what? Up to 0. This is why I am integrating from what? From this energy E up to infinity, especially for hydrogen. But this is not the case for the non-hydrogen isotopes. So the non-hydrogen isotope, I have to integrate from the lower energy that I will reach to, which is what? E, and the upper energy should be what? Somewhere here, E over what? E over alpha. And this is why I am integrating from E to E over alpha, but alpha is the alpha for each isotope, alpha J. Okay, guys? So in this case, this will be what? This will be sigma scattering for the isotope J at E prime multiplied by phi at E prime. Okay, guys? dE prime, and this will be divided by 1 minus alpha J E. Okay, guys? So this is the balance equation. The balance equation says that the absorption at this energy E plus the scattering at this energy E, scattering will take you away from this energy E. So this is sigma scattering at energy E. So the absorption at this energy E plus the scattering at this energy E is the sigma total at this energy E. Sigma total, yes.
Should that last term be divided by E or E prime?
No, divided by, by E prime, sorry. So this is the scattering plus the absorption, this is total. And if we do not have accumulation, of neutrons at this energy E, this means that whatever gets in will get out. Whatever gets in gets out. Gets out is absorption here, scattering here, which is the sigma total. What gets in from what? This energy level here is far away from fission. So we do not expect that we will have any fission neutrons that will be produced at this energy, because the energy cutoff for the fission is 50 kiloelectron volt, 100 kiloelectron volt. So I do not expect that there is neutron that will be generated from the fission at this limit here. So the only way that the neutrons will arrive to this energy bin is just by scattering from downward scattering from upper energy bins. So how I will do this? I will just look for what's the highest energy that with a single collision can bring me here. So if this is E, so the highest energy will be what? E over alpha. If alpha is 0 for hydrogen, it will be infinity. If alpha for J is alpha J, so this will be E over alpha J. And this is just, here it is. So sigma total equal to what? Equal to whatever source coming to downstairs. But because I have hydrogen and non-hydrogen, I make it to two different components. One coming from hydrogen, the other one is coming from non-hydrogen. Okay, guys? Now, if alpha J's go to 1, alpha J, in the condition that alpha J go to 1 for heavy isotopes, I do not have any contribution from those heavy isotopes, then this will be what? E to E, which will be what? 0. So I do not have contribution from here, I only have this equation remaining. But instead of just saying that it will be 0, I will approximate this as sigma scattering from isotope J at energy E prime, flux at E prime divided by E prime, because alpha J is equal to what? Alpha J is equal to what? 1 here, so I can approximate this. I can approximate this, which is this term. I will approximate this term as sigma scattering of J E phi of E. What does it mean? What does it mean? It says that because I do not depend on the heavy isotopes on moderation. There is no moderation in this situation. There is no moderation on the heavy isotopes. So all what I will say is this quantity, what's this? Total number of what? Scattering, yes? So I am saying the total number of scattering at energy E prime per unit energy is the same no matter where you are in this energy range, because it does not depend on the scattering does not depend on the type of isotopes. So this is the total number of scattering, yes, at energy E prime divided by this energy E prime. This is nearly equal to this, okay, at the energy E here. So the total number of scattering from the heavy isotopes at this energy bin per unit energy is the same like at this energy bin per unit energy. And this happens only when the scattering is negligible from the heavy isotopes. So in this case, I can replace this by what? I can replace this integral by E to E over alpha J, and this will be delta E prime divided by 1 minus alpha J, and I got outside this, which is sigma scattering at energy E, the flux at energy E, J divided by energy G, E, sorry. Okay, guys, and because this term does not depend on the energy E prime, so I can take it outside. And this will be 1 minus alpha J. And if you integrate from dE is what? The integration of dE prime is E prime. Yes, guys? E prime. Evaluated from E over alpha J, so it will be E over alpha J minus E. So this will give you what? E multiplied by 1 over alpha J minus 1. And this will give you E multiplied by 1 minus alpha J divided by alpha J. But I have alpha J will cancel with what? Alpha J, and E will cancel with what? With E, and you will end up with sigma scattering of E, phi of E over what? Over alpha J. And alpha J, I said, it's nearly what? Nearly 1. So I will have sigma scattering over J. So you will end up with all this term here. You will substitute this term. The summation of the integration will be at the end equal to sigma for J not equal to hydrogen summation for sigma scattering J of E multiplied by phi of E. So all this term here will be replaced just replaced by sigma scattering of what? It will be sigma for J not equal to hydrogen, sigma scattering J of E phi of E. This is just what I show to you guys. Okay? So sigma total is what? Sigma total is what? Sigma absorption at E multiplied by phi of E plus sigma what? Scattering of E multiplied by what? Phi of E is equal to this term here, which is E to infinity multiplied by sigma scattering for hydrogen of E multiplied by phi of E prime prime delta E prime divided by E prime plus this term. So what's sigma scattering? Sigma scattering at this energy E. Sigma scattering at energy E multiplied by the flux at energy E is coming from what? Yeah, sigma scattering with the moderator. So would be sigma scattering for what? For hydrogen at this energy E plus sigma scattering for what? For non-hydrogen, which is J. Yes, guys? As a function of E, all multiplied by what? The flux. So I just make the sigma scattering component as a scattering from the hydrogen and a scattering from non-hydrogen. Yes? And I will make it J not equal to hydrogen. So a scattering from hydrogen and a scattering from non-hydrogen. So now I can cancel. This is equal to, let's call this 1 and this is 2. So this is equal to 1 plus 2. But 2 is equal to what? I have it in this side and I have it in this side. So I can cancel those two terms with each other. So I will cancel this term with what term? With this term. And you will end up, finally, you will end up with equation. You will end up with equation like this. You will end up with equation like this. Sigma absorption is the remaining part at energy E plus sigma scattering for the hydrogen at energy E, both multiplied by the flux at energy E, is equal to E to infinity sigma scattering of energy E prime phi at E prime delta E prime divided by E prime, and this is for hydrogen. So again, to reiterate with you guys what we did, what is our goal in this lecture? Our goal in this lecture is to look for the slowing down region, try to understand what's the shape of the flux inside this slowing down region. How we will do it? The very first case is to look for just simple moderation using hydrogen, and there is still another isotopes, but they are not contributing to the moderation. What we wrote is what? Neutron balance equation. There is no time rate of change, output equal to input, losses equal to gains, yes, or sources. What are the sources? Neutron coming from higher energy to the lower energy, yes. What are the losses? Absorption at this energy, scattering at this energy. Okay? Then we do what? What we did? Here it is. Sigma total, this is the losses, equal to what? Equal to the source coming from the hydrogen scattering at upper energies, and source coming from other scattering at upper energy. Yes? Now, we stated that this alpha j is just equal to 1. Technically speaking, you will say, okay, if it is equal to 1, it's not 1, it's nearly 1. So the integral is not, the integral is what? The integral is not what? Is not 0. So the integral will be just from energy E to energy what? E over what? Alpha. And alpha is what? It's not 1. It's 0.9999, something like this. So if you divide over 0.9999, this will give you 1.00001. So this will be nearly 1.0001. So if you are integrating over a function, this is the function, and you are integrating here, but your integration is just in very small delta E, very, very small delta E. So it does not matter where is this delta E, if I integrate over delta E is here, or if I integrate over delta E is here, and the same width is the same, because this is very infinitesimal, and I can say that if you integrate over sigma scattering at E prime, multiplied by phi at E prime, divided by 1 minus alpha j, multiplied by E prime dE prime, it is the same as you integrate over E, because the width is very, very, very infinitesimal. Yes? And I can do the same integration because it is very infinitesimal. And this is what we did. And we approximated this part to be equal to what? The summation of sigma scattering at J multiplied by phi, both evaluated at the second energy. So this is E prime, and this is what? E. So this is what we did. When we did this, we approached to integral equation. This is called integral equation. So this is what? How to solve the integral equation? So there is a trick. If you have a function f of x prime and x, and you integrate over the x prime. So you have two variables inside the function, x and x prime, you integrate over the dx prime. So when you integrate over the dx prime and you have a limit here, which is a at x and b at x, you expect finally to obtain what? Another function which is called what? G. But G will be a function of what parameter? Only x. Why? Because you integrated with respect to x prime, you will obtain J of x prime and x, but you substitute for the x primes with b of x and a of x. So if you have integration like this, so now if we will obtain G of x. Yes, a final function called G of x. If you differentiate this d of x with respect to x, you will obtain the same original function. Yes, but this G of x has what? It's G of x, a of x, and b of x. Yes, because you substitute with the upper limit and lower limit. So you have this x, but you substituted with all x prime with the upper limit, which will be b of x, and all the lower limit, which will be what? A of x. So you will end up with a function G of x, a of x, and b of x. Yes, guys? So if you differentiate this function, you will return back to the same function here, but you have to take into consideration that if you differentiate this, this will give you d by dx for the upper one, b of x, multiplied by this function f of b of x and x, minus d by dx for the lower limit, which is a of x, multiplied by the same function f evaluated at a of x and x, plus the integration from a of x to b of x, and you differentiate now with respect to x, f of x prime, and x dx. So this is just when we say if we integrate a definite integral from limit a of x to b of x. So what you will do is what? Is you will get into, instead of total derivative, you will make it partial derivative for this function with respect to x, and this is this part here. And then you will differentiate the upper limit with x and substitute inside the function with the upper limit. And then, because when you evaluate the different integral, you said whatever the results of integration evaluated at the upper limit minus the same results evaluated at the lower limit, I'm doing the same. So this is the function evaluated at the upper limit, and I am now differentiating d by dx for b minus the function evaluated at the lower limit and dA by dx. If you want to do it, just, I have an example I will show to you next time that this is true. So this is just a property for if you want to differentiate a definite integral. So somebody will say, what's the hassle? Why we are doing this? We are doing this so that I will be able to solve this integral equation and transform it from integral equation to differential equation. So it's very easy. Let's look at this property here. Try to apply it to the integral equation in hand. Guys, so far, did you have any question?
So the reason we're changing it from an
Integral.
equation to a differential is because we want
To solve it.
analytic solution.
We want analytic solution. You will see how we will solve it now. So let's do it right now. So let's differentiate both sides with respect to E. So let's differentiate both sides. So the first one will be what? D by dE for sigma absorption of E plus sigma scattering of E for the hydrogen multiplied by what? The flux of E. Okay, guys? And this will be equal to d by dE for the integral from what? E to what? To infinity, sigma scattering of hydrogen at energy E prime, phi of E prime, dE prime, divided by what? E prime. So this is my function here. It's f of E prime and E. So this is the whole function here is just f of E prime and E. So when you differentiate this with respect to E, it should give you what? It should give you the function evaluated at what? At infinity. This function evaluated at infinity is 0. Because at infinite energy, I don't have anything over there. So this is 0. Then I have to substitute in this function with the lower limit will be what? E. So it will be the function, this function, sigma scattering of hydrogen at what? E, phi of E, divided by what? dE, multiplied by the differentiation with respect to E of the lower limit. What's the lower limit? And dE by dE is what? Is 1, but there is a negative sign here. Yes? Then you have to evaluate, you have to get the d by dE inside and differentiate the function with respect to what? With respect to E. This function is a function of what? E prime. If I differentiate it with respect to E, it will give me what? 0, because it is constant. So the only remaining term will be what? Will be this one. So
The E, over here in this property, you have d by dx a of x.
d by dx for the lower limit.
Oh, okay. For the, do you have to multiply by e?
The lower
here?
lower limit. So x is E. X is E. So it will be d by dE. What's the lower limit? E. So dE by dE is what?
Oh.
Is 1. And then the function evaluated at the lower limit, I will remove each E prime and I put E.
Okay.
So it will give you this term over there. So if we apply the differentiation of integral rule, which is this one, I will only, this term is the only term remaining for me. Yes, guys? Because this is evaluated at infinity, gives you what? 0. And this will be what? D by dE for certain function of what? E prime integrated over E prime. So you differentiate something which is constant with respect to E, because E prime is not E. So this will give you 0. So this term is gone, this term is gone, I have only this term. You agree with me? Okay, now I have d by dE for this finally equal to what? Equal to this. Yes? So I can, by separation, I can say that d, the total differential of sigma absorption of E plus sigma scattering of E multiplied by phi of E is equal to what? Negative sigma scattering of E phi of E for the hydrogen divided by E multiplied by delta E. Yes, guys? I just separate d by dE, I make it total differential for this, and I will get dE the other side. Guys, did you follow me? So now,
So what are you trying to accomplish here?
I try to transform this from an integral equation to differential equation so that I can solve it. Okay, guys? So now, if I divide here by this whole thing here, this. If I divide here by sigma absorption plus sigma scattering of hydrogen, this is of hydrogen, of E, all multiplied by phi of E, and then I will divide by also here by the same bracket. This will give me sigma absorption of E plus sigma scattering for hydrogen for E multiplied by phi of E divided by E. Now I will put my integration and I will put the limit. I will integrate from E to E1, for example, and this will be from E to E1. What's the first integration? Can you evaluate the first integration? What?
You just get rid of the differential operator, right?
No. This is something here. D something over something, which is dx over x. So this is what? Ln of what? Sigma absorption of E plus sigma scattering hydrogen of E all multiplied by phi of E. Yes? Is equal to this integration here. From E to E1, and this would be sigma scattering for hydrogen at energy E multiplied by dE. And I can now change the variable and make it E prime. Does it make any difference? Guys, does it make any difference if I change the variable under the integral? Why? Because it's a definite integral. Do whatever. Make it x, y, z, anything. It does not change the integration. Yes? So we cancel here what? I cancel here what? I cancel here what? phi of E with phi of E. This is why I do not have phi of E here. And there is a negative sign, by the way. Negative sign here. So now, if you will evaluate this, if you want to get this out of the len, what you will do? You will take E for both sides. So E to the len is what? Is this. And E to the power, it will give you E to the power of this integration. So now I can write, then this will be E to the power minus E to E1 sigma scattering for hydrogen for E prime dE prime divided by sigma scattering for hydrogen at E prime plus sigma absorption at E prime all multiplied by E prime. Okay, guys? Then in this side I will obtain what? I will obtain this term. Yes, guys? So if I want to separate, I want to separate only phi of E. So I have to divide what? I have to divide by this term. So this will be divided by sigma absorption of E plus sigma scattering hydrogen of E. So this will be what? Oh, but this has to be evaluated at E and what? E and E1. So I cannot do this step yet. Sorry. I cannot do this step yet. So I have to evaluate it first at E1. So the final results will be phi of E will be equal to sigma absorption at E1 plus sigma scattering for hydrogen evaluated at E1 all multiplied by the flux at E1. Then this will be evaluated at sigma absorption at E plus sigma scattering hydrogen at E, and this will be multiplied by E to the power of minus, which is, will bring all of this here. Okay, guys? Okay? I know that it's tedious, but this is how I want to solve it. So you transform from integral equation to differential equation, then use the differential equation to get the flux. And this is what we did. We transformed the integral equation to what? Not differential equation. We transformed the integral equation to integral differential equation because it has what? It will have differentiation and it also have what? Integration. This is called integral differential equation. So now let's look at this term, sigma scattering of hydrogen as a function of E prime divided by sigma absorption of E prime plus sigma scattering of hydrogen again of E prime. Okay, guys? Multiplied by what? Multiplied by E prime. This term is this term here, guys. This term is this term. I can simplify this term and I can write it as 1 over E prime minus sigma absorption at E prime divided by sigma absorption at E prime plus sigma scattering for hydrogen at E prime multiplied by E prime. Just unify the denominator. So if you unify the denominator, what you will do? Here is E prime, here is E prime, but this part is here. So when you unify them, you will take this part and E prime as the new denominator. Then you will multiply, divide all this over E prime. It will give you this part. You will put it here. Yes? And this part will be just what? Sigma absorption. So you will subtract sigma absorption plus sigma scattering. You subtract from it sigma absorption. So you will end up with sigma scattering. Just a simplification for the order of the denominators. Once you will do this, take this part, substitute it in this integral. So you will have how many integrals now? instead of one integral from E to E1, I will have one integral and another integral. So this will give me what? So this will give me what? This will give me the integral from E to E1 for sigma scattering of energy for hydrogen divided by sigma absorption of energy plus sigma scattering for hydrogen for energy, all multiplied by E prime dE prime. I will write it as two integral, which will be the first one dE prime over E prime from E to E1 minus from E to E1 sigma absorption of E prime dE prime divided by sigma absorption of E prime plus sigma scattering for hydrogen for E prime, all multiplied by E prime. What's this? Len. So yes, len. So when you take E of len, it will give you what? Whatever inside. And whatever inside is what? Is E1 minus E, yes? Because this is len E prime, and you substitute, it will give you what? E1 minus E. Yes, guys? So it will be len E1 minus len E, which will be what? Len quotient of E1 over E. Yes, guys? So when you will do this, you will have the final energy formula, flux formula, sigma absorption of E1 plus sigma scattering of E1 for hydrogen, all multiplied by the flux at E1 divided by sigma absorption of E plus sigma scattering for hydrogen of E. And now this term will give me what? E1 over what? E1 over E, e to the power of minus E over E1, sigma absorption of E1, dE1, sigma absorption, E prime, sorry, plus sigma scattering hydrogen of E prime, all multiplied by E prime. So this is the formula for the flux in the slowing down region when we have only hydrogen as the moderator to slow down, and the heavier isotopes are not playing a role. So this is the flux in an infinite medium with only hydrogen moderator and a collection of infinite alpha J's. Okay, guys? So what's this? Sigma. So absorption and scattering divided by absorption and scattering, but here is the scattering for hydrogen. So this is what? A function evaluated at E1. So it's what? A constant. And this is what? Some sigma total or whatever. Yes? Some sigma total. So the flux will be, the flux of energy will be just going to some sigma total of energy E multiplied by energy E, because this is constant. E1 is constant also. Yes? And we will look closely at this e to the power of minus whatever, the integral of e to the power of minus something, multiplied by exponential function. So you remember last time, or last couple of lectures, when I told you that the flux goes like 1 over what? 1 over E in the epithermal region. So it resembles the 1 over E because it goes like 1 over E multiplied by sigma total of E multiplied by the exponential. We will look closely for the exponential to see how this exponential can be resolved and look at a closer approximation for this one. But this is just the solution for this integral equation that gives us at the end the shape of the flux in this slowing down. So what assumption we made? Slowing down is done only by what? By hydrogen. And there is no what? There is no role played by the heavy isotopes in moderation, and their alphas is nearly what? 1. From now on, we will look for the situation where, okay, it's not only the hydrogen is the source of moderation. Hydrogen and other isotopes can play also a role. So in this case, I cannot approximate the integral sigma scattering of J, phi of E. I cannot say that it is the same at energy E prime equal at the same at energy E. So I cannot approximate it. Then we will look for, when we do the moderation, there is absorption. So there is slowing down without absorption, there is slowing down with absorption and fission. So we will look for those situations to get a clear idea of how the flux looks like in this energy region. I will stop here and continue next time. So.